In this video, we continue with examples from chapter 4.6, and we are going to be looking at how we solve systems of linear equations. So theorem 4.18 is about solutions of non-homogeneous linear systems. So earlier we saw homogeneous systems where the solution was 0. So now we're going to look if the solution is a B vector. So if x sub p is a particular solution of the non-homogeneous system ax equals b, then every solution of this system can be written in the form of x equals the particular solution, x sub p, plus x sub h, where x sub h is a solution of the corresponding homogeneous system ax equals 0. So what we're saying is every solution can be broken down into two parts that can be summed up: the solution to the corresponding homogeneous equation plus this part that's known as a particular solution. So let's take a look at the proof. So we're going to let x be any solution of ax equals b. Then x minus xp here is a solution to the homogeneous system ax equals 0, because if we take x and subtract out xp, then that's going to leave us with the homogeneous part because of this reasoning, right? X equals xp plus xh. So we've got, by matrix properties, we can say ax, matrix A times vector x, minus matrix A times vector x sub p, the particular solution. And that's going to be, well, ax equals b, and the particular solution also equals b. So that's going to be b minus b, or 0 here. So then we set our x sub h equal to x minus x particular, x sub p. And so you're left with the solution to the homogeneous part. So you have here x equals x particular plus x homogeneous. So let's take a look at an example of how this works. So we are going to find the set of all solution vectors for this system of linear equations given to us here. So the first thing to do is form an augmented matrix where we take the solutions and put them in the last column, and then the rest of the matrix corresponds with the coefficients for x1 through x4 variables. And then we're going to reduce that matrix. And so here is a reduced form of the matrix. It's not RREF, I don't think. Or it may be, because we got a 1 and 0s here. And so using the reduced form, we can construct a system of linear equations corresponding to this reduced row echelon matrix. And so we've got here x1 minus 2x3 using the coefficients here in the matrix, plus x4 equals 5. And then corresponding with the second row of our reduced row echelon form matrix. So this is an RREF. So you would do this part in SIMPy or another system. We get x2 plus x3 minus 3x4 corresponding with these coefficients equals -7. The bottom row is all zeros, so there's no equation associated with that. So we've got some free variables here. So our free variables are going to correspond with x3 and x4, because we can see our only pivots are x1 and x2. So x3 and x4 are going to be free variables s and t. And so we're going to write a representative solution vector. So if our vector x is x1 through x4, then we can say, well, that's equal to 5. So we're solving for x1 here. So this is going to be 5 plus 2x3 minus x4. But remember, x3 is s and x4 is t. So this is 5 plus 2s minus t when we're isolating x1 here. So that's where this equation here comes from. And then if we're working in similar fashion to get x2 by itself, that's going to be minus x3 plus 3x4 minus 7. Or you could say minus 7 minus all that. So that's going to be minus 7 minus s, because x3 is s, and then plus 3t, because x4 is t, so that's where this equation here is coming from. And then x3 is just s, and x4 is just t, so we write our equations that way. So if we separate this out into three vectors, we have a vector for the constants, a vector associated with s, and a vector associated with t, and each of these vectors just has the corresponding coefficients that go with s and t. So we can say our particular solution plus s times what we're going to call u1 and u2. So here what we're calling u1 is this vector here with s, and u2 is the vector here with t, and this 5, -7, 0, 0 is our particular solution. So xp is known as a particular solution of vector ax equals b, and then our x homogeneous is the second part, s times u1 and plus t times u2, and that represents an arbitrary vector in the solution space of ax plus 0. We say it's arbitrary because s and t are free variables. You could have any values there for them. So that brings us to theorem 4.19. So this is about solutions of system of linear equations. So the system ax equals b is considered consistent if and only if b is in the column space of A. Remember back from chapter 1, a system is consistent when it has at least one solution. So let's take a look at the proof here. For the system ax equals b, we're going to let a, x, and b be the m by n coefficient matrix, the n by 1 column matrix of the variables, and the m by 1 right-hand side. So if we want to label our diagrams here, here's our matrix A, and here's our vector x. And then if we multiply through, we've got x1 times the column vector here, a11 through am1, and x2 times the column vector a12 through am2, all the way through xn times the column vector a1n through amn. So ax is going to equal b if and only if the vector b, which is b1 through bm transpose, is a linear combination of the columns of A. So in other words, that is, the system is consistent if and only if b is in the subspace of Rm spanned by the columns of A. And so that's because our b here has to have m as its length, if that makes sense. So when they say transpose of the row vector here, they might as well have just said b1, b2 through bm as a column vector that this is equal to. And that makes sense because b is the length m, so it's going to have to be in the subspace of Rm. So let's take a look at this example. So consider this system of linear equations. If we create the augmented matrix using the coefficients from the first set here on the left side, the three equations, and then augment it with the solution over here, B. Here's our augmented matrix. So notice that B equals 2A1 minus 2A2 plus A3. So let's go ahead and write that out. So -1, 3, 1 equals 2 times 1, 1, 3 minus 2 times 1, 0, 2 plus just 1 times A3 here, which is -1, 1, -1. And we can check, okay, 2 minus 2, that cancels out, and then plus a -1 matches for our first value of B. For the second value of B, 2 times 1 is 2, minus 0, we're still at 2, plus 1 more is 3. And then for our third value of B, the 1 here, 2 times 3 is 6, minus 4 from the 2 times 2, so we're at 2, and then minus the -1 over here, right here. Then we get the 1 for the third value of B, so that checks. So then B is in the column space of A because it's a linear combination of those three vectors, the column vectors of A, and our linear equation is consistent because it has a solution. So here's a summary of these equivalent conditions that we've seen for square matrices. So if A is an n by n matrix, then these conditions below are equivalent. So some of these we've seen in earlier chapters, and then the last three conditions here are new for this chapter. So we know A is invertible is equivalent to saying AX equals B has a unique solution for any m by 1 matrix B, so essentially any column vector. AX equals 0 has only the trivial solution. A is row equivalent to the identity matrix of n dimensions. The determinant of A is non-zero. We know that is equivalent to A being invertible. The rank of A is going to be n. That makes sense because it's row equivalent to the identity matrix in n dimensions, and the rank corresponds with the pivot columns, and so those are going to correspond with the identity matrix dimension. The n row vectors of A are linearly independent, and the n column vectors of A are linearly independent. So if you have one of these conditions, remember to come back to this list because all of these are equivalent, and that will help you in problem solving.